Hello everyone. In this session we are going to see about wireframe modeling and surface modeling in partial. These topics comes under Unit 2 Geometric Modeling in the paper of ME 8691 Computer Aided Design and Manufacturing. So straight away let us go into the presentation. So first of all, what is meant by wireframe modeling? So this type of modeling uses points and curves to define an object. As we can see in the slide, I had mentioned a part. I had mentioned a part diagram, and this part diagram can be visualized as wireframe, which is nothing but wireframe modeling. So we can see that V1, V2, V3, V4, etc. These points are called vertex, which is nothing but endpoint. And what are all the two endpoints connecting is nothing but edge, which means the two end points is connected to make an edge. E1, E2, E3, E4 are edge. So this is nothing but wireframe model of advantages of wireframe modeling. So with the help of wireframe modeling, we can able to convey information quickly and efficiently than multi-view drawings. Multi-view drawings is nothing but plan, elevation and all. So with this wireframe modeling, it can be directly used in finite element analysis. With the help of finite element analysis, we can able to analyze the thermal property, harmonic analysis, like and all. So, and it can also be used as an input for CNC machine to generate simple parts. Here simple parts, so not a complex parts, which means these simple parts does not have any complex shapes or curves, and it contains most of the information needed to create surface, solid and higher order models. So this wireframe modeling gives the surface information, more likely to say with the help of vertex and edges. So what are the disadvantages of wireframe modeling? So it does not tend to be realistic. So it only shows the vertex and the edges of an object. It does not show what the solid look like. So how the core of the object will be. So it does not show that parameter, and so it is not so realistic. It does not represent an actual solids, that is no surface and volume inside the solid object. So and complex curved surfaces cannot be modeled through wireframe modeling. So and so we cannot able to calculate the dynamic properties of an object. Ambiguity is nothing but it cannot visualize the entire object in a clear manner. It only shows the outermost surfaces, edges and vertex of an object. Complex model is difficult to interpret with the help with this wireframe model. So that ambiguity property is nothing but from this model. So let us consider this as an example. So here it can be visualized by two means, either a cubic solid object inside in a glass container, or else a complete solid object with a hollow cube inside, which is nothing but core. The core is hollow. So it may be interpreted by these two kinds. So ambiguous views means the outermost views. So A, B, C, D is nothing but phase 1. So this is one type of interpretation, and this one is another interpretation which does not shows the interior or rear side vertex and edges, and this one is the third interpretation which is viewed through another angle. So with this wireframe modeling is over, and let us go inside surface modeling. So a surface model represents the skin of an object. These skins have no thickness or material type. As the name defines, surface, it only represents the topmost layer of an object. So what is meant by surface modeling? So it is more sophisticated than wireframe modeling, in that it defines not only the edges of a 3D object but also its surfaces. So being the definition of surface modeling, it does not shows the edges of an object but also the skin of an object, which is nothing but surface. In surface modeling, objects are defined by their bounding faces. So faces means the combination of 4 edges made to form surface, so which is nothing but bounding. So what are all the advantages of surface modeling? So as wireframe modeling provides more ambiguous views and non-uniqueness, and it can be eliminated from this surface modeling, and renders for the model for better visualization and presentation, objects appear more realistic. So surface modeling renders more realistic objects appearance than the wireframe modeling, and also it provides a surface geometry for CNC machine. And in terms of mold and die design, the most important thing is the surface geometry. So mold and die design requires the surface, how the surface looks like. So that geometry is provided by this surface modeling, and it can also be used to design and analyze complex free formed surfaces. Complex free form, which means the simplified curves can be visually seen through surface modeling. So and also the surface properties such as roughness, color and reflectivity can be assigned and demonstrated. So in this surface modeling, the roughness, color and reflectivity, etc., these are all surface parameters, and it can be assigned and demonstrated in the surface modeling. So disadvantages of surface modeling. So this surface models does not provide any information about what is present inside an object. If a flaw is present in a solid object, it cannot be viewed through this surface modeling, and it cannot be used to calculate dynamic properties. Curves are used to represent the surface of an object. And how the curves can be represented? So we have to know about the types of curves. What are all the types of curves? Explicit curves, implicit curves and parametric curves. So in explicit curves, we can able to view the equation in the slide, y is equal to f of x, which is nothing but here x is independent and y is dependent variable. So as far as x value differs, y value also differs, and it can be also stated that the functions depends on 2 variables. And another one, implicit curves, which is also a non-parametric curves. Function of x, y, z is equal to 0. We can able to view the linear parameter in this equation. And the third type of curve is nothing but parametric curves. In this parametric curves, the function is converted into coordinates, or otherwise it can be stated that a point is mentioned as a coordinates, and the coordinates of the points can be identified through the parameter t. Here we can able to see that x is equal to x of t, y is equal to y of t, and z is equal to z of t. Here t is nothing but the parameter. So from this parameter, a range is fixed. Through this range we can able to identify the points, which is nothing but coordinates. From this coordinates we can able to derive the function. So what are all the types of curves? Analytic curves versus synthetic curves, which is nothing but synthetic curves is also a type of curve. So analytic curves represents points, lines, arcs, circle, fillet and chamfers. So from this we can able to represent that analytic curves is very simple in manner or simplified. So synthetic curves includes types of splines. So types of splines includes cubic spline, B-spline, beta spline and Bezier curves. So this is the example of implicit and parametric curves, which is nothing but the classification of curves. As I said already, the implicit curves x square plus y square plus z square minus r square is equal to 0, and z is equal to 0 as because of we are representing in 2 dimension, and so the third dimension z is equal to 0. So in this diagram in the slide we can able to see that x, y and z. So it is not a 3-dimensional representation, so z is equal to 0, and considering x and y and the theta is nothing but the angle. So the beginning of the angle will be 0 and end of the angle will be 360. So with this angle we can able to identify the radius, and whatever the x and y we can able to represent a point on the circle. So a point on the circle with the representation of x and y coordinates and also with the radius, this representation is nothing but implicit curve. And in terms of parametric, the theta is nothing but the parameter. If the theta varies and also the x and y component value will also vary, which is nothing but a parametric curve. So with this one example we can able to define both implicit curve and parametric curve. Basic concepts includes the curve and other parameters, order of continuity and degree of continuous derivative. So order of continuity is nothing but the term usually used to measure the degree of continuous derivatives. So order of continuity is nothing but how many times the equation can be differentiable, which is nothing but order of continuity, and degree of continuous derivatives is nothing but while differentiating the parameters generates our degree of continuous derivatives, which is nothing but C0, C1, C2. Here it is represented. So there are basically 3 parametric continuity, which is nothing but 0 order parametric continuity, first order parametric continuity and second order parametric continuity. So what is meant by 0 order parametric continuity? So consider this diagram. So the 2 curve section must have same coordinate position at the boundary point. So this is the same coordinate position at the boundary point. So in this curve this is the boundary, and in this curve this is also the boundary. So these two curves have same coordinate points. So if so, this type of curve can be considered as 0 order parametric continuity. And consider the second example, first order parametric continuity. Tangent lines of the coordinate functions for 2 successive curve sections are equal at their joining point. So tangent lines, so consider this as a starting point. So for this curve, this is the successive curve, which is nothing but the curve next to the previous curve is called successive curve. So end of this curve, the starting point of this successive curve will be originated. So in this point there will be a tangent. If we draw a tangent for this curve, it also ended in this point, and also if a tangent drawn for this curve, it also ended in this point. So for 2 successive curves a tangent lines originates, then it will be a first order parametric continuity. And second order parametric continuity, both the first and second parametric derivatives of the 2 curve sections are same at the intersection. We have to keenly notify that both the first order and second order parametric derivatives nothing but first differentiation and the second differentiation. Both this first and second derivatives of the two curves, this is one and this is another curve, are same at the intersection. Then it will be noted that second order parametric continuity, and it can be visually seen in this example C2. And then basically a curve can be drawn through interpolation and approximation. So what is meant by approximating curve and interpolating curve? So in this diagram, approximating curve, we can see that point P2 is left and P1 is left, P3 is also left, P0 to P4. A sinusoidal waveform is pattern is followed, and in this interpolating curve, no point is left out. All the points were included in the curve. And convex hull. So convex hull property ensures that a parametric curve will never pass outside the convex hull formed by the four control vertex. So if a curve is drawn, so consider this as a curve, there will be four control points, four or more control points. So convex hull property is nothing but a parametric curve will never pass. So approximating curves defines the convex hull. So a curve will never pass outside the convex hull. So these 4 points are the control points of this curve. So in this approximating spline, the curve does not pass out through this control points, and in this case interpolating spline, a curve is passed out through the control points. So curves includes entities. So surface curves include surface entities, and this surface entities is classified into analytic entities and synthetic entities. So plane surface, ruled surface, surface of revolution, tabulated cylinders or comes under analytic entities. Hermite curves, B-spline curves, Bezier curves, Coons patches are comes under synthetic curves, which include synthetic entity. So plane surface. So plane surface may be either a single plane or multiple plane. So the word plane describes two-dimensional, either xy, yz or zx. And second one, ruled or lofted surface. This is a linear surface. It interpolates linearly between two boundary curves that define the surface. So this is the curve number 1 and this is the curve number 2, and this ruled loft surface interpolates linearly between two boundaries. So this is the linear interpolation of these two curves, which comes under. And third one, surface of revolution. This is an axisymmetric surface that can model axisymmetric objects. So consider this as an axis and this is a planar curve. So these are all in two dimension, and it generates by rotating a planar wireframe entity in space about the axis of symmetry a certain angle. So in this case throughout 360 degree. So here the angle will be 360. With the help of this axis, this planar curve is rotated throughout this 360 degree, and hence we can able to get this entity, which comes under surface of revolution. And the last one of analytic entities is tabulated cylinder. So this is a surface generated by translating a planar curve through a certain distance along a specified direction. So consider this as a circle in the two-dimensional plane. So this circle is converted to cylinder by dragging this plane to either this direction or this direction. It can be seen in this diagram. So a curve must not be circle only. It can be either this type of curve or this type of curve. So if you project these curves towards the direction, either this direction or this direction, we can able to get this type of surface entities. And with this we can end this session, and in the next session we will see about the synthetic curves. which includes Hermite curve, Bezier curve, B-spline curve, Cones patches. And with all these things, we can able to conclude the surface modeling. And then in this unit, we will have to see about solid modeling, which includes CSG and boundary representation. We can see all these things in the next consecutive presentations. Thank you.